Lab 1 go okay? Should have been due last Friday. I think most people were able to finish, so great work on that. Lab 2 is due this Friday. Anyone done with Lab 2 yet? Okay, just a couple people. Please start Lab 2 as soon as possible. Today, I'm actually going to walk through a lot of Lab 2 Part 2. So that is what we're going to be doing. Look forward to that. I'm also going to talk a little bit about Lab 3, which will start with soldering. So you should have all received an email on how to sign up for the soldering workshops that will be led by Bells. So yeah, please look into that. There are soldering irons that are in the lab, and please, solder your boards as soon as possible. Even if you're maybe still working on Lab 2, solder your boards. The reason for that is because there may be a big backlog of students like trying to solder at the same time. So, let's keep our voice down. Yeah.
I'm sorry, I didn't catch. Are we allowed to solder at home if we have?
You may solder at home. Yeah, totally allowed to. Yeah. I recommend just doing it in the lab though. So let's keep our voices down. Okay. Okay. Here is my board. You probably have this exact same board, except you probably don't have all these pins here. It's probably just flat. And if you notice, you'll see there's tiny little look like little bulges right there of metal. Anyone know what this is? Yeah, so this is solder. So this is some low melting point metal alloy, but it's a really great conductor. And the whole point, it's you can think of it kind of like super glue, except instead it's like a highly conductive metal, so it can actually connect like the actual like copper traces on this printed circuit board to whatever devices you want to connect to the board. And if you look at this board, if you look at like all of these little devices, like this little capacitor and resistor and the Type-C port, you'll notice that there's actually little bits of solder on every single one of these. That's how circuit boards are actually created. Is first I guess you like etch a bunch of layers of copper and put them together, and then put a big like kind of layer of plaster on the top and then silk screen. And then it's like a nice like looking printed circuit board. Then what you do is you attach all the little devices, so all the capacitors and resistors. Usually this is done by like a pick and place machine, and you'll have like maybe this industrial assembly line thing where it will pick up this tiny little capacitor and it'll go and put it down perfectly, and then it'll like put them all there, and then maybe there will be some sort of like solder paste, and it'll melt all of the solder all in one go in like an oven, and then it'll magically kind of make everything perfectly aligned. Anyone do soldering kind of in the past before? So there we go. This is how printed circuit boards work. You may like wonder, it's like how did they get the little like devices on it with this metal? So, it's a low melting point metal, and they can kind of just melt the metal to like grab onto the devices and make it all work. There we go. So in Lab 3, you will have to actually solder the pins on here. Soldering is just a really important skill. Most jobs in the real world, you're not going to really need to solder very often, but sometimes you do. And either way, it's probably a good skill to know. Also, if you ever want to do any like electronics repairs, maybe it's like a birthday present for like your friends, like you want to replace the like battery in their iPod or something, and you need to like desolder the battery or something. Learning how to solder is just very, very important skill for all computer engineering majors. So I have a short little slideshow presentation that I want to quickly go through just so we're on the same page on soldering. There is a workshop, so hopefully this will either be a review from that if you've already gone to that, or it will just be a good preparation for that. We'll just kind of skim through it. It's a long slideshow, but I'll just do like a little bit of it. Okay, you may notice we have this very charismatic guy right here. He's actually holding soldering iron incorrectly. So this is a soldering iron, and the idea, you're right. The idea is, so there's this really hot like iron at the top with it's very, very hot, and solder, if I remember, melts at 650 degrees Fahrenheit. Am I getting that right? I don't know. It's very, very hot, and so if you touch this metal part like he is touching, then it'll burn you. Probably won't hurt because it'll like burn you so quick that it'll fry your nerve endings. So it probably won't hurt, but it'll hurt a lot as it heals, like over the next few days. So be very careful not to touch it. It's totally safe though, as long as you hold it from the plastic part, kind of just stay away. Also, I kind of sometimes will like to wear a mask and then also like glasses, because sometimes there can be like splashes that happens and you don't want it to like get on your face. Very rare, but like, can happen. Okay, so the idea with solder, yeah, so here is like copper, here's copper, and then you put some sort of like low melting point metal in between so that now you have a really strong connection. There we go, solder. This is what soldering looks like zoomed in. So this is, you can see the solder is sucked around both copper, like the wire, and also the trace. This is what it would look like if there was no solder. Okay, yeah. Okay, so in order for solder to work well, so the solder needs to like first melt and then like attach to all of the metal. So everything needs to be very hot and also very clean in order for the metal to properly grab onto things. Because if something's too cold, then it actually won't be able to stick to it. If something has dirt on it, then it also won't be able to stick to it. Solder is kind of this magic thing where it will kind of just like suck itself onto whatever clean metals are nearby. Cool. So probably the biggest problem though with solder is oxidation. Because like I said, so your soldering surface actually needs to be kept extremely clean in order to attach the solder to it. But if you heat up anything, or if you ever get anything wet, specifically metal, then you will have oxidation, which is like rust. Like if you leave a bike out in like the warm summer where maybe it like is really humid, then that bike will rust extremely quickly. It's the exact same thing with soldering iron. If you heat up your board, then what's going to happen is there's going to be oxidation. Same with the solder itself. The solder, like sure, it like can act as a liquid when it's really hot, but as it's really hot, it will also get like this layer of crust on it. So that means that you actually just need to go like extremely quick. You don't want there to be any rust buildup. So soldering, like the longer you take, it's like, oh, it's not working, it's not working, it's not working. After a while, what will happen is it just won't work anymore because there's too much like rust over the top of it. So it's kind of, you gotta go fast. The faster you go, kind of the better it will work. So this is what will happen if there's oxidation. You can see the white border is saying it's like it's not able to, the solder is not able to stick. Yeah. Okay, good. However, there is this magical material called flux. And I don't really understand exactly how it works, but effectively what it will do is it will dissolve away rust. So very handy. So oftentimes you will have solder. So this is how solder is presented. Like you can buy solder at like hardware stores or online from electronic stores. And it comes in a big spool, almost just looks like wire. And so here's like a really zoomed in picture of this wire. You can see like here's the spool right here. And you can see that there's actually a flux core, meaning inside there's a little like gel that as you melt this solder down, then there will be flux that will be dispersed onto the solder and also the printed circuit board in order to dissolve away the oxidation. You can also you can find solder as well as like a little pen that you can just kind of scribble onto your board, and then it will also rub away some of the rust. It can also come in like this, this gel that you can kind of put on. There's different forms of flux, and they're all pretty much the same. Okay, so there we go. So this is how you would use flux, is you would coat the pins in flux, and then now all of the oxidation dissolves away, and now the solder can actually properly connect to the copper. Cool. This is what flux looks like when it is on your solder tip. It will like smoke, and it looks kind of cool. And so it's kind of interesting because like the more smoke you see, generally that means like the better your solder connection is going to be, because it means that there is solder, or there is flux like working its magic and dissolving away the oxidation. But that also means that it's giving off like an unhealthy gas, and so you actually don't want to breathe this in. And also like the longer it gives off the smoke, that smoke will eventually go away. So when you see no smoke, generally that means that you're out of flux and your solder joint like will not work anymore. Cool. Okay. Feel free to stop me at any point. You'll also, this will also be reviewed in the soldering workshop by Bells. But good. Cool, and then so here is a good solder connection, and you can see here's some residue flux, and it's totally fine to keep on the board, but usually people will go and clean it off with like isopropyl alcohol afterwards to make it look a little prettier and be less sticky, because it's kind of sticky. So, good, okay. So, I guess thinking ahead, so if you heat up metal a lot, what will happen to it? It's going to rust, it's going to oxidize, okay? Now the solder iron itself, when you heat that up a lot, then what is going to happen to it? It's also going to rust. So the soldering iron itself is going to start rusting as you use it. So probably the most important thing, maybe even more important than you like burning yourself, because like if you burn yourself, like, skin grows back, it's like, it's not too big of a deal. What is a big deal is if your soldering iron rusts, because then you have to go and like buy new tips, and it's kind of expensive for bells. So what is better is you actually when you're done using the soldering iron, so you actually want to coat it in another layer of solder. And that will act as kind of like a protective layer over top the soldering iron. I wonder if there's a diagram of that actually. Yeah, so it'll look like this. So here's the soldering iron. So you'll go and put some of the solder onto the soldering iron. You'll poke it on, and then now the soldering iron will have a little bit of solder on its tip. And then when you're done soldering, you just want to make sure that there is still like solder on your tip, and then turn off the soldering iron, let it cool off. And it can take like 10 minutes to cool off. And then by the time it cools off, then there should just be a big soldered glob on the tip of it in order to protect that tip from oxidation later. Okay, cool. Good. So I think that's probably a good enough kind of introduction to soldering. Please go and sign up for the workshops. You can also find like cool YouTube videos of people doing like micro soldering. People get like really, really into soldering. Soldering is how all printed circuit boards are assembled. So yeah, it's very cool. Any questions about soldering? Happy to go more in depth, but I feel like probably I could leave it to bells, because they'll actually give you like practice and hands-on experience with it, versus me, I'm just giving you a slideshow. So, yeah, any questions? Yeah. Okay, good stuff. Last class, we began talking about I2C. Today, I want to go a little bit more in depth on the actual example code of running the I2C example. Has anyone successfully gotten the I2C communication working with the temperature sensor? Okay, then this should be very insightful for you, and I expect you all to be taking really good notes, because I'm basically going to show you how to do part 2 of your lab. Cool. So I found this example. So this is an example code from the ESP IDF, and so I went into examples, and then in peripherals, here we can see I2C, and then I2C basic, and I opened up main, and so this is the basic example that it gives us. So very cool. So we can see that we have to set the pin for the clock pin and the data pin, and here we can set the frequency, and then here are the ESP IDF functions that it gives us to kind of abstract away actually sending things out over I2C. So if you remember, right, so I2C, serial communication, so it takes place over basically just like the single data wire and then the single clock wire to tell you when to sample. And what you probably could do if you wanted, and some people will do this, is they will do something called bit banging. And bit banging is when you do GPIO write 1, and then GPIO write 0, and GPIO write 1, and you intentionally will send out ones and zeros by changing what the GPIO value is. And we could do that, but the issue with that is that's probably going to be fairly slow, because GPIO writes and reads and anything dealing with GPIO is going to be fairly slow and timing inaccurate. What happens if maybe in the middle of you sending write 1, write 0, write 1, write 0, maybe right in the middle of that, something happens where maybe your operating system, because our ESP32 is actually running a very bare bones operating system. Maybe the operating system is going to context switch out of that sending process, and now it's going to run some like other like error handling code or something. And that would be catastrophic for us sending our serial communication, because yeah, right in the middle, if we just decided to like chop off, like it's like, oh, like actually like instead of sending like 101010, right in the middle of that, I'm going to wait for like 100 milliseconds or something. That's totally something that could happen. So therefore, instead of bit banging everything, instead of just sending things out on GPIO, instead we can use the actual like baked in functionality that ESP gives us, where we can set like internal like configuration registers that will send out the I2C data through the ESP pins. And we can just say like, oh yeah, like configure it to this frequency, configure it to this data, configure it to this address, and then it will send it to the ESP. Then in hardware, the ESP will send out that data. We don't need to write like actual code to say like, oh, send this bit, send this bit, send this bit. Instead, we can just say like, oh, send this command, and then it will do everything for us. And that is what, and this command, like we could go and like write to like actually like the memory mapped IO addresses, but probably the better way is to just use the ESP IDF functions that are provided to us. So here's the basic example, and here is probably so to me, like I'm just looking at this, these functions look like the functions that ESP IDF gives us that lets us actually use that hardware functionality to send out the data over I2C. So I'm going to open up these functions. So I just held Control click, and so now I can see like what this function is. And actually, so I can see, so this is the I2C master.c, but I actually want to check out the header file instead, because the header file will probably have like the documentation of it. So here I found in advance, I found the I2C master.h file. In my opinion, this is even better than reading like the documentation on the website, because this is like the actual source code. Like we know that the source code is going to be correct, but we don't necessarily know that the documentation on the website is going to be correct. So yeah, just in general, always looking at the source code of any library is probably going to be more useful than looking at the documentation of a library. That's just my personal opinion. Okay, cool. So here we have I2C master receive. Now, okay, it looks like this will perform a read transaction on I2C bus. Okay, well, let's see if we can find the write. Well, okay, so I2C master transmit. So it looks like this is performing a write on the I2C bus. So if you remember, so there are two modes that you can be in. The host or the master can either do a write or can do a read from a peripheral. So it looks like these two functions are probably going to be the main functions that we want to use. Here's the write function, so I2C master transmit, and then here is the read function, this I2C master receive. See, it does a read transaction. Cool. Okay. Let's quickly look at what it takes in. So we can see it takes in I2C dev. Okay, well actually this is stumping me right away. So it looks like I2C master dev handle T. I'm not sure what that is. If we want, we can do Control click and like look up what this is. And okay, it looks like this is this type, and I can try opening it and say, okay, so this is I guess whatever this object is. I could also just look back at the example code. So here we can see, okay, so it takes in this dev handle object, and now I can search for this and see where this is created. Okay, dev handle. Okay, dev handle looks like it takes it in. Oh, here we go, dev handle. Okay, and dev handle is assigned where? Looks like it's assigned right here. Okay. So it looks like this object right here, this dev config, dev handle object, this is what goes into it in order to like properly configure this. And now we can go and use this inside of both our like I2C master transmit and our master receive. Okay, let's go and actually fill this out. Okay, so our address width, does anyone know what our address width should be for the temperature sensor?
7.
What was that? 7, yes, so it should be 7. We can find that in the documentation. Honestly, most things have an address of 7. It is also possible to have an address of 10. If I go and, actually I can go and control click on this and I can see, so I just control clicked on I2C address bit length 7, and now I can see like what other values we're allowed to have. And yeah, okay, so it does look like it has support for 10-bit address widths, but only if we have enabled, I guess, this flag right here. Okay, sure, cool. So, okay, this looks good. But here, instead of this NPU9250 sensor address, we should probably put something else instead, because instead we want to access the address of our temperature sensor. So, okay, I want, if you happen to have your laptop out, really quickly go and pull up the Rust board, like documentation, and figure out what the address of this is. Or maybe you just remember it from last class. Okay, go and tell the person next to you what this address is. Okay, so here is the Rust board, and I can see, so here's the temperature and humidity sensor. And what is the address of this? This is 70. Great, okay. So what I will do actually is I will rename this. And I'll just name it that, okay. Cool. Just fixing this. So this address is now 70. Okay. Good. And then the frequency here, let's see where this is set. Honestly, we could just hard code this so that we're not worrying about configs. So does anyone remember what frequencies we can run this at? So if I go and open up the data sheet, let's see. Anyone see it? See it? I can search for hertz. Let's see. Cool. Okay. So 400 kilohertz, I guess, to 1 megahertz. Okay, let's do 400 kilohertz. So 400, 1, 2, 3. Is that right? Yes. Okay. And so now it looks like we have configured our device correctly, in theory. Let's go and see what this other config is for. So it looks like this is, I2C port. Honestly, not sure exactly what this is. So we can probably skip this. Or actually, I do know what it is, but we can skip it in this example. Okay, so then the IO num. So it looks like this is, so the data and the clock pins. So let's make sure that this is correct. So, okay, so the clock pin. So anyone remember what the clock and data pins are on our board? Okay, let me quickly go and pull it up. So, okay, anyone see it? What is our clock pin number? Yeah, so this is going to be GPIO 8, and then our data pin is what? 10, yep, and I just found it right here. Good. Okay, so now we have properly set this, and we'll clock source. I don't know, we can click on this and see, well, you know, we'll probably just go with default. That's probably fine, not sure what those are for. Glitch ignore count. So maybe this is for like internal kind of error checking. So this is probably fine. And then enable internal pull up. Probably just want to keep it to whatever the example is. I think we'll go over what the pull up resistor is for in a bit. So okay, there we go. So we have now properly filled out the master init. So now the question is, what do we do? What did we do last time when we were like just trying to learn what this temperature sensor, like how to communicate with it? What did we do? So there's a cool page on the documentation. So if I scroll. Okay, I'm going to scroll through kind of slow. Let me know if you see a page that is useful. Oh, which one? This one?
Yep.
Okay, I highly agree. This shows you exactly the commands and things that you would need to send in order to receive all the data properly. So we can see here it sends out the data. Here it sends out the address. We probably don't need to worry about that because we've already set the address right here. Okay, but then it sends the wake up command. So wake up MSB, wake up LSB. Okay, let's go and now add a function that will send a command. So we can probably ignore these functions for a second. Let's call this whatever, ESP T. So it can return the error type just like this, and then we can do maybe the name of the device. So this is the temperature, humidity temperature sensor, and we'll do send command. As uint16, we'll do command. Okay. So here is a 2-byte number, and we can tell it's 2 bytes because I've set it to 16 bits here. And that is, in fact, the length of the commands that the temperature and humidity sensor expects. So the first thing is sending this wake up command. So we can see first it sends the most significant byte, then it sends the least significant byte. So let's go and create a buffer for this. So I'm going to go and separate this out. So I'll call this, I don't know, data. Yes. Or maybe, yeah, that's probably fine. Okay. And we'll make this have a width of 2. And so what, actually, okay, we'll come back to this. So we're going to put something in here, and it'll probably be something like the upper byte of command and then the lower byte of command. So it'll be something like this. But now let's look at what the documentation is for the internal ESP IDF function that we need to run. So okay, what function would you expect we need to run in order to send a command out to the ESP? Yeah?
The transmit?
Exactly, yeah. So it'll be this transmit. So I'm going to go and grab this. And I will bring this down. Yeah, that's fine. Come on. Okay. So cool. It looks like we need to pass in dev handle as well. So we can go and grab that. And probably also, was that it? Okay, that's fine. Oops. Dev handle. Okay. I guess I can put that over here. And we also, I guess, need the write buff. And I assume that is probably just data. Okay, so the question now is if we wanted to send this data, I guess now we need to worry about this endianness. Because here, so we need to send the most significant byte, then the least significant byte. But here it's not immediately obvious, if we send out this data, it's not immediately obvious, how, which byte will come first. Okay, what do we do? How do we find out which byte will come first? Yeah?
The diagram that says the most significant byte should come first?
Yes, but how do we find out what, basically, how do we find out what to put in here? Because we don't know the order at which, this function will send out the bytes. You should probably just go into this function and check out the documentation of this now. So, okay, so I can check out transmit. Okay, and there's transmit. Okay, do we see any sort of order here? Anything? No. Yeah, actually, not seeing anything. Okay, well, in this case, we will probably just need to try it both ways. So, okay, let's, I don't know. Which one should we do first? Should we do the most significant byte first or least significant byte first? Yeah. We can choose either, because we don't know the order at which they'll be sent. Okay, let's do the most significant byte. So in order to do that, so we can do command, and then we want to probably shift it. So we'll shift it by how much to get the most significant byte? What was it?
8.
Yeah, probably 8. Okay. And I will go and cast this to probably a uint 8. This will probably help. Okay. And then next, what do I put here? So here is the most significant byte, and then here should be probably the least significant byte. So what do we put in these parentheses to grab the least significant byte of this? Command? Okay. Do we need to do anything else? Actually, yeah, so this will truncate it off. We might get a warning though, so I will want to go and AND it with something. What should I AND it with in order to chop off like the top byte? Okay, yeah?
15.
Not 15. Okay, yeah?
X, F.
Not hexf. Close.
X, F.
FF, yeah, exactly. FF is 1 byte. If I just did one single F, this is half of a byte. This is considered a nibble. I don't know if you've ever heard that. Yeah, so this would be 1 byte. So if we wanted, we could also do something similar here. Say and OX FF like 0, 0. And then shift by 8. So we could do the same thing here. This is probably not as important though. But okay, cool, good. So I don't know. We can do like a to do check this is correct. Okay. So what's next? Maybe we should do the read as well. So the read will probably be fairly similar, except instead of master transmit, so we could do master receive. And does anyone remember what the temperature and humidity sensor will like return once we request data from it? So how many bytes will it return? Okay. That's okay. We'll quickly pull up the diagram. Okay, so here it looks like, so after it does the command, the measurement command, so it'll do a measurement command that says like, hey, please give me your data, and then the temperature and humidity sensor will wait for a little bit. It'll do the calculation, perform everything. It'll wait like some amount of time. Then finally it will be ready. So then when the host performs a read, it will then respond back with how many bytes? Yeah, it's 6 bytes. It's these 6 bytes. So in this example, so it will first return humidity MSB, humidity LSB, then a checksum for the humidity, then temperature MSB, temperature LSB, temperature checksum. This is specifically for the commands that it happened to choose. You can send different commands that will format the data slightly differently, but no matter what, it will always return 6 bytes. So okay, in that case, then I'll just make a quick comment. So read 6 bytes. Okay. So I'll rename this maybe like read data or something. So good, so we probably pass in the dev handle Maybe we should also pass in the like temperature, like where we want to store the temperature data. So we could pass in maybe like a pointer, uint16 star temperature, and uint16 star humidity. Did I spell temperature wrong? I think so. That's good enough for now. Okay. And good. So the data, so it's going to be 6 bytes. So let's go and load in the data into this like data array right here, and we can just default it to all zeros if we want, just for fun. Okay. Now we need the master receive. Notice that this is master transmit receive. This like code, this example code project, and I think that this is just a little bit confusing. It might speed things up a little bit. You're welcome to try playing around with it, but I personally just like the more basic, just I2C master receive command. So yeah, we can go back into this and find it. Where is it? Yeah, master receive. Okay, here are the inputs to it, I guess. Wait, oh, good. Keep this commented out. Good, okay. So it's going to return this error thing right here, so we can go and save it, and then we will go and bring this all down to a new line. So the dev handle is just going to be passed straight in. The read buffer, we can pass in data. Okay, the read size is going to be 6. It can also be like size of data if you want. And then here's a timeout, and we can grab the same timeout from this down here. Okay, what is the purpose of a timeout? Was that?
Doesn't hang forever.
Sure, when would it hang? So remember, what is expected is when you do a read command, here I can go and send it. So when you do a read command, it will first, like the host will send out the address, and it will say like, hey, I want to do a read. And this is what it will look like. It'll send out an address, and then it will send out like this read bit. Then what it expects is on the next clock cycle, the peripheral should immediately start returning back data. So if the peripheral like immediately starts returning back data, then why would there ever be a case where we would need to have like a hang? Because like it should be like just on the next clock cycle, it immediately returns that data. So in what case will we have something hang? Yeah.
If the data is not ready yet from the sensor?
Not necessarily, right? Because like if the data is not ready, it's possible that the sensor may just respond immediately and say, hey, my data is not ready. On the next clock cycle, it might just say like, hey, I'm not ready. Yeah. In what case will you have the have the peripheral like somehow like stall the host? Okay. Yeah.
Does it have to do with the clock stretching of the peripheral?
Exactly, clock stretching, right? So the idea with clock stretching is that the peripheral can override the clock value. So the host is like trying to change the clock. It's trying to be like, give me the data now. Like I'm sampling you right now. What the peripheral can do is it can write the clock line to 0. Like it can just override it no matter what. And now the host is not able to like rise it high. Like the host is not able to sequentially like, make the clock continue. So, okay, in that case, so only in clock stretching, you actually really care about this I2C master timeout. Usually, this does not actually matter, and you can set it to -1 or whatever you want. But yeah, so it's important for clock stretching. Okay, and then good. So then after we receive the data, then now we would need to go and put it into temperature and humidity. So I think I can probably leave that for you to do. So you could probably just imagine you take data and then you probably grab like maybe 0, like maybe the 0th element of data corresponds with, well, I guess it's kind of unclear. Maybe the 0th element of data maybe is this one, or maybe the 0th element of data is this one. I'm going to guess that this is probably the 0th element of data. So maybe you can take like the 0th element of data and then concatenate it with the first element of data, because this is the LSB, and then that will then produce the raw temperature data. And then you can do the same for humidity. So I will go and, just for now, I'll just go and set them to, actually I'll do OX, I don't know, 1, 2, 3, 4. This is OX, 2, 3, 4, 5. Questions on this? Okay. Okay. Are we learning? Absorbing? Frantically taking notes? Confused? There we go. Yeah. I2C. So the point of this lab, so yeah, first you want to read out the data over the I2C bus. Then you will go and process this data, because this temperature data that's actually returning is going to be given to you as this 16-bit value, but that's not this is not temperature. It's not like Celsius, it's not Fahrenheit. So what you will need to do is look into the documentation to see how to interpret this temperature data as a human readable format. So that's something in the documentation. So there's just a simple equation. You have to do a division and multiplication. You just use floating point numbers. Yeah, so go and check out that. Okay, write it to do. So I want to take a step back and think more about the purpose of pull-up resistors. So I just found this picture on Google Images, and it's pretty good. So yeah, here you can see, here's the I2C bus. You can see you have a host device connected to a bunch of peripherals. You could potentially even have another host device, but in this class, just imagine that you only have one single host device. But then, yeah, you also see that you have these two resistors here, R1, R2, that pull up. Actually, this is incorrect. I don't know why. Okay, well, maybe this is the best. But imagine that R2 actually is also connected to the clock. Okay, imagine that. Okay, good. R2 also connected to the clock. What is the purpose of this? Why do we have pull-up resistors? Can't the peripherals and the hosts just write 0 when it wants or write 1 when it wants? Why do we need resistors like this? Yeah.
It's because there's sometimes noise in the line. Scatter.
Absolutely. That is a very good point. Yeah. So sometimes you have noise, maybe this wire can act as an antenna or something, and maybe it will just pick up random charges from the environment. Pull-up resistors are really great at dissolving away any sort of static electricity. If you have a button, usually you'll see pull-up or pull-down resistors on a button, because when you disconnect a button, it's possible that the other side of the button may count as a capacitor, and it will actually keep whatever value it had just seen. It will keep storing that. So even if you let go of the button, it might still stay high or something. So yeah, absolutely. What is another reason for having why pull up resistors? Yeah.
Kind of to have a reference voltage for the ones and zeros. Otherwise, neither would know where the 1 0 is.
Sure. Okay. I like that. So yeah, having a reference voltage so we know what a high voltage is. I would say the main purpose, though, of having pull-up resistors is now, if there are ever two devices that are writing to the same line at the same time, now we are not going to get a short circuit. Because now the only thing that the hosts and the peripherals need to do is just drive the signal low. But you will never actually have a host or a peripheral drive a signal high. Instead, that responsibility falls entirely to the resistors. this is good because like imagine you have a peripheral that's sending a logic 1 that's like hooked up right to VDD, like it's a battery, and then another peripheral is hooking it up to 0. Then yet you have a short circuit, and now potentially your wire could burn, and it's going to use up a lot of power. Instead, if you have now like 2 devices that are trying to communicate at the same time, the only thing they're doing is just writing zeros. And so if you have like a host writing 0, then at the same time you have a peripheral writing 0, then that's fine, because they're both just writing 0, so it's not a problem. There's no sort of short circuit. And then if one of them lets go of the bus, if one of them stops, then the signal will still stay low because of the other like device sending something out. And then when that then releases the bus, then both signals will go back up to 1 volt, which is totally fine, because like if by default, if nothing is touching the clock wire or the data wire, then the default signal is expected to be 1. And so if I'm a peripheral and if I'm like sniffing this device, if I'm not driving it, but I'm just reading it, and I see like logic 1, then that tells me that like nothing is writing. But if I see a 0, then that means that something is like currently writing to the bus. And that is the reason why the acknowledgement bits, if you remember acknowledgement bits when we were going into like the actual like analog voltages of the wires, that's why the acknowledgement bits were 0. That's why also like the start bit was 0 and the stop bit was 0. Like everything that the host and the peripherals can do it's all they can do is just choose to write the signal low. Yeah, kind of cool. Honestly, pretty genius. This helps with power reasons, helps with speed reasons, contention reasons. Is there an issue though with resistors? Like why do we not use this in like a computer chip with like billions of transistors? Why would we not want to use resistors on like on a bigger chip like that? Why is it fine when you only have a few devices, but like it's not a good idea when you have like a large chip? Why do we not like resistors? Yeah.
There would just be passive power draw.
Exactly. Yeah, right. Resistors take up a lot of power. The only thing that resistors do with the voltage that is flowing through them, the only thing they're doing is they're just converting it into heat. Resistors are like actually generally frowned upon. Like you never really want to just throw resistors on things because it will just create like unnecessary power drop for no reason at all. And in fact, like if you have that was honestly one of the big reasons that computer chips have gone from using aluminum inside of like their interconnects and like on a chip. Like instead of having aluminum wires, instead now we've moved to copper wires. So like you can have like copper wires that are a few like nanometers across, and in that case, like you really need to make sure that you have something that has a very low resistance. Just resistances in general are just like very bad. So, okay, let's do a quick calculation for fun. So imagine now, let's see, am I good? I'm good now. Okay. So the question is, let's say we were just continually like oscillating this signal. Maybe this is modeling us sending out like just an insane amount of data for like indefinitely. Like it's like I2C transmit, I2C transmit, I2C transmit, like over and over and over and over and over. The question is, if we have a coin cell battery, which is about 1 watt hour, so 1 coin cell battery, and we've seen coin cell batteries before. Okay, they're kind of the most typical battery that you'll see in embedded devices. So they last for about 1 watt hour. And the question is, how long could a device last if it was just continually sending out I2C signals? Okay. So here is a potential like I2C line. So imagine we have a 1K pull-up resistor, right? And then we have some sort of maybe transistor or something that is then pulling this wire down. And so the question now is, what current will be flowing through the transistor in order to effectively pull this down to 0 volts? Okay, notice we're at 5 volts. So if this was open, if this was like an open wire right here, then this would be 5 volts right here. Right? If this was open, this would be 5 volts. Good. Okay. Good. No one's nodding. If this was open, this would be 5 volts. Okay. Now the question is, if we immediately go and close this, then what is the current now, like through this circuit? Okay. So current would be, I believe, like voltage divided by resistance, right? So this would be, then what? This would be, I believe, 5 milliamps. Okay? So 5 milliamps is just going to be always activated anytime we are drawing the signal low. Okay. Imagine now half of the time this signal is going to be low because we are just continually oscillating between 1 and 0. Okay, so half the time this is going to be low. And now imagine that there's 2 wires. So okay, so now imagine that we are effectively drawing 5 milliamps continuously forever. Okay, then how long can we last if our battery capacity is 1 watt hour? So how do we go from milliamps here? How do we go from milliamps into watts? Yeah, so this is the power through a resistor. So sure, so this is the milliamps, but actually to find the amount of power that we have is this would be, I guess, 25 over 1K. So this would be, I believe, 25 milliwatts. Yeah, I think that's correct. Okay, so if we have now 25 milliwatts continuously being drawn from our system. So I'll go and draw that out. Okay, so 0.25 number of watts. And if we have 1 watt hour, okay, what do we do? How do we do this? 1 watt hour. So maybe if we want to find like the number of hours that this will take. So I think it'll just be like 1 divided by this. So this is the number of hours that our device will work for. So 40 hours. There we go. That's not very good, right? 1 single coin cell battery. Potentially coin cell batteries could last like several years, like potentially like 20 years. So if we wanted, we can now do a computation that's like, okay, well, how many I2C like signals could we send out if we wanted to like last over 20 years? So that's another computation that we could do. Sure. We're not going to do that right now. Could be a quiz question. Okay. Any questions on this? Okay. Good. Yeah, question.
Could you explain how you got that one?
Yeah. So this is the amount of power that we would be drawing if we were just continually sending I2C transmissions. So this is how much power we are drawing. And if we wanted to now find the number of hours that we could run for, assuming that we only had 1 single watt hour total. So if we have 1 watt hour, then we would divide it by the total amount of power. And so we can run that 1 watt hour battery for 40 hours at this power. Yeah, thank you. Okay, well, I think that is good enough. It seems like you are all experts. No more questions. If you have any questions, feel free to come up. I will see you on Wednesday, where we will continue talking about Lab 2 and also Lab 3.